So as Dhruv promised you yesterday, I'm going to embed the tropical M0n today and show you that it actually is a balanced fan. And in order to embed the M0 trop n, we use the distance function. This pen is really great, huh? I don't know who was it from you who got that, but thanks a lot. This is really nice. So we use the distance function from M0 n trop first to r to the n choose 2. And what this is, you know, the elements in here are marked tropical curves. Yeah, I'll actually draw a concrete example. For example, the length of this bounded edge could be 1. Then we have some marked ends of infinite length, right? And they are marked with 1, 2, 3, 4, let's say. And we map such a gamma, so gamma EG, right? EG, this picture. Gamma goes to the vector that records the distance between the ends I and j at the coordinate ij. And when I say distance, what I mean is the sum of the length of bounded edges that connect those ends I and j. Yeah, we're talking about the rational case here, so there's a unique path going from end I to end j, and I sum over all the length of the bounded edges in that unique part, and that is what I want to call the distance between end I and end j. So let's be really precise in this example. So if n is 4, as in this example, then n choose 2 is 6, and we can label those 6 coordinates as 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. And then what is the distance of this tree gamma? You know, end 1 and 2 sit precisely together at one vertex, so I don't need to cross any bounded edge. The distance is 0. If I go from 1 to 3, I have to cross over that one bounded edge of length 1. If I go to from 1 to 4, the same. 2 to 3, the same. 2 to 4, the same. And 3 and 4 are sitting right next to each other, so that's 0 again. Okay, oh yeah, and one thing I wanted to point out is that you can think of this function really also as the tropicalization of the Grassmannian. So Dhruv told you yesterday that you can take the Grassmannian, take the Plücker embedding, take the Plücker vectors inside the Grassmannian, and if you take those and tropicalize, then the image of my distance map, this is precisely what you get. Yeah? So the image of the distance map you can view as the tropicalized Grassmannian. And this operation of taking distances precisely corresponds to taking valuations of Plücker vectors. So for all of you who are very interested in matroids, I think this is a useful comment, because you can view the tropical Grassmannian, of course, as all possibilities to put valuations to a matroid, right? Valuated matroid, and from my point of view, is nothing but a tropical linear space. And now I'm talking of tropical linear space for which I fix ends in a sense. Yeah? Okay, so this is what that is. But now, you know, since we're doing M0n and not the Grassmannian, we have to mod something out, which is sort of the torus action that showed up in Dhruv's lecture. And what we have to mod out is the following. So let's define the following map, phi, from r to the n to r to the n choose 2, that sends our vector just to the sum of its coordinates, ai plus aj, ij. Right, and you know, just to have an example, phi of E1, let me, just to keep track of the coordinates, label those coordinates again, 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. And then what is phi of E1? So 1 So, okay, E1 is 1, N is for 1, 0, 0, 0, right? So 1, 2, I have to add 1 and 0. Here I have to add 1 and 3. Now I have to add 1 and 4. Now I have to add 0, 2 and 3, 2 and 4, and 3 and 4. So I get 1, 1, 1, 0, 0, 0.
Do you care about the ordering?
No. You mean whether it's 1, 2, or 2, 1?
Yeah.
No, it doesn't change anything. Neither concerning the distance, nor concerning the sum here. Yeah. I just, I don't want to have them both. Just, yeah. But the ordering is not relevant. Okay, and one other way to think about that is you can think about it, let me put this in quotation marks, as the distance of something that we don't really consider in the tropical world, but something that sort of has a 2-valent vertex. 1 on one side, and 2, 3, 4 on the other side, and a length 1 bounded edge in between. We wouldn't consider that, right? Because it's not stable, you can say. Or an alternative way to say this is, ends are supposed to have length infinity. So this is not really a tropical curve, but you can think about it like that. And the reason why I make this comment is because I want you to realize that sort of this, so we're about to mod out the image of phi, right? To embed our M0n bar, not in R to the n choose 2, but in R to the n choose 2 minus n, yeah? In R to the n choose 2 modulo the image of phi. And the reason why we want to do that is because we don't want such guys, right? So the extra thing that you have if you are in the tropical Grassmannian are sort of possibilities to have length on the ends, which are not just infinity and which are not just ignored. Okay, so right, so some notation I want to use. If I have a subset of 1 up to n, which is of size bigger or equal to 2 and less than or equal to n minus 2, then I want vi to be the vector which is the distance of a tropical curve that has the ends marked I on one side, everyone else on the other side, so I complement on the other side, and length 1 in here. Yeah, so for example, this thing I could call V12. I could also call it V34, of course, yeah, because it doesn't matter which I call I and which I call I complement. Okay, and then if I have any tree gamma, E and H of gamma, I want removing this H provides a partition of the ends that are on one side and the ends that are on the other side. Yeah. Let IE be the ends on one side. Let me put it like this. And then the distance vector of gamma is the sum over the length of my edges times the VIE, where the sum goes over all bounded edges. And that's pretty easy to see. I don't want to prove this. I want to sort of prove by example, because that actually works, I think, in that case. So let's look at one combinatorial type, or one tropical curve, I should say, in M05, markings 1, 2, 3, 4, 5, and 2 lengths for my bounded edges L1 and L2. Okay, and I claim that, yeah, so this is my gamma, okay, and I claim that my distance of gamma is equal to L1 times V12 plus L2 times V12. well, I could just write V45 here, I guess. V45, yep. And you can view this as, you know, again, quotation marks, write something in pictures. So this is, you can view this as the sum of this tropical curve with length L1 here, plus this one with 1, 2, 3, 4, 5, and L2 here. Yeah. So we're focusing on L1 first, shrink every other edge. That produces this ray, or we focus on L2 and shrink every other edge to produce that ray. Okay, and as I said, we should, at least in this example, actually prove this. So let me write down all the coordinates for M05. 1, 2, 1, 3, 1, 4, 1, 5, 2, 3, 2, 4, 2, 5, 3, 4, 3, 5, 4, 5. Okay. And now what about the distance of gamma? And then next, what is V12 and what is V45? And you know, we'll fill out this table, and I claim that filling out this table, you already observe what is going on, and you sort of see that this statement is actually true. Okay. So let's try to do this. In gamma, to go from 1 to 2, you need 0, both here and here also. Okay, to go from 1 to 3 in gamma, you cross over the L1 edge. Okay, so it's L1 here. To go from 1 to 3 in here, in V12, sorry, it's just 1. In V45, it's 0. Okay, to go from 1 to 4, we have to cross over both. So it's an L1 plus L2 already. It's a 1 here, and it's a 1 here. 1 to 5, same thing, right? L1 plus L2, 1 here, 1 here. 2 to 3, L1, 1, 0. 2 to 4, L1 plus L2, 1, 1. 2 to 5, L1 plus L2, 1, 1. 3 to 4, just L2, 0, 1. 3 to 5, L2, 0, 1, 4, 5, 0, 0, 0. You see it works, and I believe you see why it works, right? Okay, then this may be not completely obvious, but it's a fact that if we view distance from M0 in trop into R to the n choose 2 mod the image of phi, that this is injective. As I say, this is not completely obvious. A big part of the proof is to show that trees of which are not of the same combinatorial type cannot have the same image. Once you saw that, then you can sort of restrict to life within one combinatorial type, and then it's not so bad, because in a sense, then you see already if you vary length parameters, of course you're changing your distance vector, right? So the biggest part is sort of to convince yourself that if you have different combinatorial types, you will also have different images. And you can do this by some sort of induction. So for every combinatorial type, you can find something which is called a Sherry. A Sherry is a vertex that has 2 marked ends which are adjacent. And then you sort of need to find cherries for which your 2 combinatorial types disagree. And then you'll have zeros at different locations and so on. Okay, the image of phi is, of course, something to pay attention to also. Earlier, I just said, you see that I vary something in the distance vector when I play with the length. Of course, you have to make sure that also when you mod out the image of phi, this is still going to be different. But that's sort of back to this idea. Yeah, modding out the image of phi means you're changing length on your ends, which we don't really have. So that's fine. Yeah. But let's just believe that this map is really injective. Right? And now I want to show, so then once I know this map is injective, I can sort of identify the M0 entrop with the image in here. And what I want to show is that this is actually a balanced fan. Yeah? Meaning that it has tropical structure, which is what we want our moduli spaces to have. This is what makes them nice, right? Okay. to speak about something being balanced, I need to give you an integral structure also, right? I need to tell you what the lattice in this vector space is going to be. And it's actually not the standard lattice. So I want the lattice spanned by all vectors of the form Vi to be my lattice. Be the lattice of R to the n choose 2 mod m phi. Yeah, meaning those vectors which correspond to tropical curves that look like this, yeah, they are sort of the unit vectors, yeah, they are the vectors in my lattice. Okay, and now we have a theorem that says M0 n-trop viewed as living inside R to the n choose 2 modulo image of phi is a balanced marked fan of dimension n minus 3. And what are the markings of the rays? Well, what is a ray in M0 n-trop? I need to give you a combinatorial type that just gives a one-dimensional orthant, right? Because we know that M0 n-trop is glued from orthants, and the orthants have dimension number of bounded edges in my combinatorial type. So what is a ray? A ray is precisely a picture like this, with just one bounded edge. So the rays correspond to those vectors Vi, right? And I want the Vi, the vectors Vi, of course, to be the markings. Okay, so where the Vi are the markings of the rays. Okay, and we're going to prove this. And for the proof, we're now going to use all the preparation that we did last time. Yes, please.
So isn't that lattice exactly the different lattice?
No, it's actually not. It has some higher index, 2 to the something. It's not, yeah.
But all the Vi only appear, there are only one, right?
That's right, yeah, but nevertheless, I mean, the 1, 1, 1, minus 1 vectors in R2 also span a lattice of higher index, right? Yeah.
So the weights of M0 n-trop are not one of them?
No, they are. And this is why I want to fix this to be my lattice, right? So your question is actually, it's a good question, it's interesting, but I'd like to take the perspective that I actually don't care, right? I don't care what this lattice has as with kind of index with a normal lattice, because I don't care about the normal lattice. This is my reference lattice. And since this is my reference lattice, all the cones will have weight 1.
I agree with you, but so they are different.
Yes, yes, they are different. The normal lattice is different from this. But nevertheless, my cones have weight 1 because I declare this to be my reference lattice. It's actually, it's just a convention. You can do it differently. Yeah. I like this way because I like the Vi vectors. I find them rather natural. Anyway, right, so this is now where all the preparation will be used that we had last time, because we showed last time that in order to see that a marked fan is, if marked fan is balanced, all you need to see is the sort of easy version of the balancing condition for which you don't need to look at normal vectors where you need to convince yourself that you span a lattice basis and so on, right? All you do is you sum the markings of the neighboring cones of your codimension 1 cone, and you need to find that this is 0, right? And this is what we'll do now, and this is where the preparation will be used. Okay. Right, let's first discuss a little more the structure. So this theorem also claims that it's a balanced marked fan of dimension n minus 3. That it is of dimension n minus 3 yet again is of course not surprising, because we already know that the maximal cones in our M0 n-trop are of dimension n minus 3, because we can have at most n minus 3 bounded edges. And it's also true that M0n is pure of dimension n minus 3, because every maximal cone has this number of bounded edges. We also know that it's actually simplicial, because every top-dimensional cone will be generated by those VEIs, right? Sorry, VIEs, yeah? By the V's that correspond to your bounded edges. So if I have n-3 bounded edges, then I also have n-3 ray generators for my cone, yeah? And that means that I'm a simplicial cone. I have as many generators as the dimension is. So let me just write this down. M0n trop is simplicial, so that the notion of a marked fan makes sense at all. And the top dimensional cones, dimension n-3, are spanned by n-3 rays. Okay. So we need to show balancing, so we need to study codimension 1 cones. What's a codimension 1 cone? That is a cone in which I have one edge less compared to the maximal type. So if I change the perspective, if I start with the maximal type, I need to shrink one length to be in codimension 1. And if I shrink one length, then I produce exactly one 4-valent vertex. Yeah? I'm 3-valent everywhere else, but I have exactly one 4-valent vertex. So tau, cone of codimension 1, corresponds to combinatorial type with one 4-valent vertex. So here's a sketch, local sketch of how this tropical curve looks like. Here's a 4-valent vertex. And then this thing continues somehow, I don't know, right? But I don't care. This is my 4-valent vertex. And I label the ends that I can reach via this edge as the ends A, subset A of 1 up to n. These are the B's, C's, and the D's. Okay, there are 3 top-dimensional neighbors. Of tau. And what are those 3 top-dimensional neighbors? Well, they just correspond to the 3 ways to insert, yet again, a bounded edge, to resolve that 4-valent vertex into 2 3-valent vertices. So I can have A with B, CD, or AC, BD, or AD. BC. And yet again, these are all local pictures. The actual combinatorial type somehow continues, but I don't even need to know how it really continues. So the 3 vectors, which are the new vectors, I mean, this cone is spanned by n-4 vectors, which are of the form VIE for some bounded edges in here, right? And then the additional ray, which is needed to span this neighboring cone, is precisely VA union B. And here VA union C and VA union D. These are the 3 markings of the 3 extra rays which span my 3 neighbors around this codimension 1 cone. So this is tau, so to say. Those are my 3 neighbors, A union B, A union C, A union D. I have those 3 vectors pointing inside those rays. Okay, now I consider a curve in the boundary of gamma, in the boundary of tau, sorry. Let gamma be in the boundary of tau. All lengths except those 4 edges shrink to 0. Yeah, so what I'm saying is I'm taking, everything that is happening out here I ignore and just let those ends be ends here. Yeah? I look at the curve that looks like this. Okay. this doesn't move, right. Then I pick A in R to the n, such that AI is 1 if xi is at the 4-valent vertex. And 0 else. You know, these edges don't have to be bounded, right? Could be that, for example, D is just a subset consisting of 1, yeah? D equal I, yeah? For some end xi is hanging right here at the 4-valent vertex. This is precisely the situation where I would call my AI 1. This is sort of a correction vector that will allow me to write down one precise equation. So it's true that VA union B plus VA union C plus VA union D is the distance vector of precisely this tropical curve gamma plus phi of A. And this is true in R to the n choose 2. And once you see this, yeah, the theorem is proved. Yeah, why is the theorem proved once you see this? Because what you have to show is that your sum of marked vectors is 0 modulo the span of tau, but this guy lives in the span of tau, and this is 0 anyway because we're working modulo the image of phi. So once we show this, we have showed our balancing condition and we're all set. And this is honestly just a computation. So you're just following coordinates and checking that the ij's coordinates agrees on both sides. Yeah. So maybe we can do it for one case. Just to put a bit more structure, this is actually a claim. And what we do is check this equality for all coordinates ij in this R to the n choose 2. Now, you know, there are cases, right? Because ij could be anything. Ij could be both part of A, or I here, j here, and so on, right? So there are some cases. Let's just do one case. One case. Let's consider what happens if ij subset A. That's actually the boring case, sorry. Anyway, let's just discuss it quickly. If ij are both in A, then, well, all those three vectors will have a 0 at ij because the distance, this edge is never crossed, right, to go from I to j. And in gamma, you also never cross any of your 4 edges. That's it. So this case is just 0 equal to 0, and we're okay. Yeah, that's a boring case. Let's do a more interesting case. Let's do I in A and j in B. Then what is the distance in gamma of ij? So I is somewhere here, j is somewhere here. We have to cross over those two edges. The only question is, are those bounded edges or not? If A only consists of the end I, then this is not a bounded edge. Then I have just one edge, right? So this is going to be 2 if both A and B have more than one end. It's 1 if A or B just have one end. Yeah, so for example, without restriction, if A only consists of xi, and it's 0 if they both have only one end. If A is I and B is j. Okay, what about the phi A of ij? Okay, so AI is 1 if we have an end, and it's 0 else. So phi of A is 0 in the first case. It is a 1 if A or B have only one end. And it is 0 if A is I. And it is 2, sorry, it is 2 if A is I and B is J, because then AI is 1 and AJ is 1, and the sum AI plus AJ is 2, of course. And now what about the V's? VA union B, IJ. Well, I go from somebody in A to somebody in B. If I do that here, yeah, I'm not crossing the bounded edge. So that's just 0. VA union C, IJ, that is 1, because now I have to cross, because I have to go from A to B. And VA union D, IJ, is also 1. And now we just put this together, and we see, we get 2 on the left side of the equation, and no matter in which case we are in, we also get 2 on the right side of the equation. And that's it, actually. And, other cases like 2 guys in B or 1 in B, 1 in C are sort of just the same, yeah? So this is actually the proof. Now we know that this guy is really a balanced fan. And what we gain is, of course, well, you all know that I like M0n, but I really care for the space of tropical stable maps, right? But the space of tropical maps is just an M0n trop times R2, yeah? Because we only need to know one image point to be able to reconstruct the whole tropical map. And so once I know that this is a balanced fan, I also know that the same holds true for M0n of R2 delta. So you could call it a corollary. Anyway, M0n trop of R2 and some degree delta is a balanced fan. And where does it live? It lives in R2 times R to the, number of n's, which is n plus elements in delta, choose 2, modulo the image of the corresponding map phi. Okay, and now we know that the parameter space for our tropical stable maps is actually a balanced fan, and this is quite nice, right? What is the next aim? The next aim is to show that those numbers of tropical curves we are counting are actually intersection products, tropical intersection products on this tropical parameter space, which is now a balanced fan. Because what do we know so far? We introduced our numbers. We know that we have to count tropical curves or tropical stable maps with multiplicity. And we talked about this multiplicity in 3 different ways, so to say, right? One was the nice combinatorial way, product of areas of triangles in the dual subdivision. That is the useful one somehow that you want to work with later. The second was the big determinant, but the big determinant was coming from local coordinates. I sort of restricted myself to one combinatorial type and made some computation in there, right? And that's something, those 2 are equal, we know, yeah? And then we always claimed that this big determinant is also equal to some lattice index, and that this lattice index has something to do with this guy being a balanced fan, right? And this is what I still need to show. This is where I'm going now, yeah? In order to do that, I need to tell you a little more in general about tropical intersection products or degrees of tropical maps. So let's step back a little bit. This is one big achievement. Let's be happy about this big achievement. Let's take a step back and learn a little more about fans, map of fans, and so on, in order to then come back to this and discuss these multiplicities again. Okay, so let's just talk about two fans, sigma 1 and sigma 2. Fans in R to the R, respectively R to the S. Sigma 1 pure of dimension n. We consider a map from the support of my first fan to the support of the second fan. And I call this a map of fans. If it is set linear. So be careful, this is quite a bit different compared to the toric world, because I don't actually care about the fan structure. That's something that Dhruv also already told you. For me, it's not so important how those cones are subdivided. So I don't care whether cones are mapped into cones or something. What I really need is the integral structure of this map. I need this to be a global set linear map in order to have those well-defined multiplicities. In order to produce those multiplicities, I'll define a so-called image fan. I call it F push forward of sigma 1 in sigma 2. And what should it be? It should consist of all cones, of all image cones, F of sigma, okay? Such that sigma lives in a maximal cone in sigma 1 on which F is injective. That might not at first, if I try this just like that, it might not be a nice fan because the cones don't have to fit nicely. But I can always produce a subdivision of sigma n such that this works. Yeah? And I don't care, so I subdivide as much as I must in order to produce something such that this collection of cones is actually a fan. And what is important to me, I don't like cones which are smashed by F. Yeah? If F is not injective on a cone, forget about this cone. I only like to keep those which are sort of treated nicely by F. So I take only those maximal cones on which F is injective, and of course I take their boundaries also, because I need to make an honest fan, right? So possibly subdivide sigma 1 further in order to make this a nice fan. Okay, and then, if F is not at all injective, then I might just have defined the empty set. That's not an interesting case. It works, right? But it's not interesting. But if F has cones on which it is injective, then these image cones will, of course, be of the same dimension. So in this case, which is the case which interests me, I know that this thing is a pure n-dimensional fan. Now in R to the S. Yes?
What's the problem? Why could that not be a fan?
Why could that not be a fan? Those images might overlap somehow. And then you have to subdivide further to avoid this. Okay, so we produced an image fan. The one example that I really care for of a map between fans is the evaluation map. I know maybe this is a bit of a lie, because as soon as I want to prove Konsevich's formula, I have to sort of vary the context slightly. But nevertheless, a prime example is the evaluation map. So you can always have this in your head as the example where we are actually going with this somehow. So now we want to define weights for our image fan. Weights for the image fan, push forward of sigma 1 of such a cone, sigma prime, in the image. What we do is we'll sum over all cones in sigma 1 that hit this cone, such that f of sigma is sigma prime. Then we take the weight of the cone sigma in sigma 1, and then we take a lattice index times the index of span sigma prime in set to the s modulo the image lattice f of span sigma intersect set to the r. In that way, we make this image fan also a weighted fan. Yes, please.
I just got kind of lost. What is the sigma prime again?
That is just a cone in f star of sigma 1. Just a cone downstairs. A top dimensional cone. Sorry, I think your confusion arises because I'm using not so optimal notation. Sorry. So where is it here? I sort of used the same notation for cones in sigma 1. Maybe I shouldn't have. But, you know, let's just process this and then forget the notation, okay? So here, you know, sigma prime were the top dimensional cones in sigma 1 and sigma, their boundaries, so to say. Now let's forget this. And now sigma prime is a top dimensional cone in f star of sigma 1. Yeah? And then, of course, this top dimensional cone is hit by some guys in sigma 1. I call those sigma now. Sorry. Okay, let's do an example. Let's do a baby example. Let's not start with a moduli space of tropical curves, or maybe we do in a sense, because I'm just drawing a line now. Tropical line. So I call this cone sigma 1, sigma 2, sigma 3. All weights are 1. With one glance, you all realize that this is, of course, a balanced fan in R2. So that's very nice. Let's take the following map from R2 to R, just the projection. X, Y goes to X. Of course, that is a set linear map, no problem. How does the image look like? It's just going to be an R, which has two cones. Let's call this sigma 2 prime and this sigma 1 prime. F restricted to sigma 3 is not injective. So this cone will just be forgotten in our image construction, right? F of sigma 1 is sigma 1 prime. F of sigma 2 is sigma 2 prime. The span of sigma 1 prime intersected Z is just Z. The span of sigma 1 intersected Z2 is just 1, 1. The span of 1, 1, right? But f of the generator of this lattice is just 1, which is a generator of this lattice. Generates Z. Okay. So that means that the weight of this cone, the weight in this push-forward fan, is 1. Yeah? And a completely analogous argument here. Sorry, this is actually not true. This is -1, 0. But that's the statement is still true. And this was actually the reasoning for why this weight is also 1, right? So the push forward is going to be the subdivided line with two cones of weight 1. Okay. I want to vary the map to give you a bit more exciting example. Now let's take, let me actually do it like this. X plus Y. F is the map X plus Y now. Of course, the image is still just, lives in R, but let me draw it differently, just to keep track of the projection, so to say. This is my R now. And it's true that F of sigma 1 and F of sigma 3 are both equal to, let me call it sigma 1 prime. And this is sigma 2 prime. And F of sigma 2 is sigma 2 prime now. So that replaces this statement here. Now what about the weights? let me talk about this guy. It's still true, it's spanned by the 1, 1 vector. And f of 1, 1 is now 2, right? And that does not span the lattice Z. 2 spans a lattice of index 2 in the standard lattice of Z, right? So the lattice index is 2. And so the weight we obtain in the push forward of sigma 1 for this cone sigma 2 prime is 2. 1 times this lattice index, which is 2. On the other side, for the other cone, sigma 1 prime, I have 2 guys that meet it. They are spanned by -1, 0 and 0, -1. They both go to the generator in Z, right? But there's 2 of them. So I have a sum of 1 times 1 plus 1 times 1, right? So the weight of the push-forward fan of sigma 1 prime is 1 times 1 plus 1 times 1, which is also 2. So here I have a 2, here I have another 2. So that's nice, because what seems to be the case is that this image fan is also a balanced fan, right? The original fan was, the image fan was, no matter how we project it somehow. And this is actually no coincidence. This is actually true. And this is our next statement. Though the proposition is the push-forward fan is a balanced fan if sigma 1 is. Okay. To get a feeling for timing, let me check the watch. Yeah, okay. Maybe I don't really want to prove this. It's yet again somehow a hunt of lattice indices. There's a question?
When you write the ZS, so DR,
Yeah.
so in the example of M0 and top, no?
Yeah.
The lattice was not Z to DR.
No, that's right. The lattice of that space. Yeah. Replace set to the S by the lattice of your vector space. Yeah, thank you. Good point. Very good point. Yeah. Right. So, you know, an exercise in lattice index hunting. I hope that the example tells you more than seeing me go through another lattice index hunt. Let me not prove this now. Let's move on and define the next notion. I believe the proof appears in Renzo's notes about this course, right? I think you spelled this out. Yeah. So, and you all have those notes available. So in one of the next free working sessions, respectively exercise sessions, if you want, you can also use some time to go through this and ask questions if anything is unclear, right? Okay. Next definition. A balanced fan sigma 1 is irreducible if for all balanced fans sigma 2 of the same dimension whose support is contained we already have equality of the support. meaning I don't have an honest subfan, which is also balanced. So let me start with a non-example. This thing is not irreducible because this is a subfan of the same dimension, which is balanced, but it doesn't have the full support. Yeah? So this is not irreducible. Okay, the tropical line is irreducible. Try to only get away with a strict subset of those rays, it doesn't work. You need to be balanced, you need to have all the rays, that's it, right? So this is irreducible. There's nothing like a unique decomposition in irreducible fans. This guy, you can view it as this, union this, or you can view it as this union this, right? So we don't have something like a decomposition into irreducible subfans, but we do have irreducible fans. And with those irreducible fans, we can do something nice concerning those maps. So here's a lemma. If sigma 1 and sigma 2 are balanced fans of the same dimension, such that the support of sigma 2 is contained in the support of sigma 1, such that sigma 1 is irreducible, then we can deduce that sigma 2 is sort of a global multiple times sigma 1. How do we prove this? It's just an idea, which is pretty clear, I think. Well, first we can deduce, because of the irreducibility, that the supports are equal. Okay, once the supports are equal, I can refine and assume they actually have the same cones. I can subdivide, refine, such that sigma 1, sigma 2 have the same cones. Now, the only thing that differ potentially are the weights, right? I can have some weights in sigma 1 and some other weights in sigma 2. So I let lambda be the minimum over all top dimensional cones of the weight in sigma 2 divided by the weight in sigma 1. If this is not already an integer, I can sort of multiply with the denominator to make it an integer. And then I can define a new weight function. I can define a new weight function on this fan, which is possibly multiply times the denominator and then omega sigma 2 minus lambda times omega sigma 1. Okay. Now this new weight function is built in such a way that there are cones for which it is 0, right? But cones of weight 0, I can throw them out of the support. I can treat them as if they are not there, because they don't contribute to any balancing condition, right? They will produce a summand of which is 0. I can just erase them. But then that means that if something was left, that would be a strict balanced subfan in my sigma 1, right? Strictly contained balanced subfan in my sigma 1, which cannot be the case because sigma 1 is irreducible. Yeah? So the new weight function, gives a balanced fan of support strictly contained in the support in sigma 1. So using irreducibility, it must be empty. And so we can deduce that for all cones, we actually just have this one global factor for the weights. And yeah, the thing is proved, right? Oopsie. I just multiply with the denominator.
So then the difference is in 0?
Yeah, yeah. Put the denominator here. Yeah, good question. Thank you. Okay, so we still have 5 minutes. This will not be sufficient, I believe, to prove the next theorem, but I can at least state it and say something, and maybe we can talk a little more about it next time then. But I think it's very important to write this down at least to keep you on track, to tell you where we are going with this. Okay, so what is the next statement that we want to show? If sigma 1 and sigma 2 are balanced fans of the same dimension, we have a map of fans from sigma 1 to sigma 2, and sigma 2 is irreducible. Okay, then there exists a fan which I call sigma 2 0, which is contained in the support of sigma 2, which is of smaller dimension. And you can think of those of the walls. We are about to make a statement about the degree of f, and the degree of f is measured in terms of counting inverse images, and we should count inverse images somehow only in the interior of top dimensional cones, and these are going to be the walls. This is where we should not count. So the statement is, there exists this fan of smaller dimension such that if I take a point Q, which is not in a wall, okay, a point which is not in the wall, then they are in the relative interior of a top dimensional cone, which I call sigma q prime in sigma 2. That's maybe not so surprising yet, because that means I just take the codimension 1 cones of sigma 2 out, but I'm actually taking more out because I want that all pre-images, all P in F inverse of Q, are in the relative interior of a top dimensional cone which I call sigma P in sigma 1. And then for a point like that, I can define what I call the degree of f, and it's going to be the sum over all pre-images all p such that f of p is q, the multiplicity of f at p, where the multiplicity of f at p is defined to be the weight in sigma 1 of sigma p divided by the weight of sigma 2 of sigma q prime I called it, sorry, to make sure it's in the image, times the usual lattice index, the span of sigma q intersected SID S modulo f of span of sigma p intersected Z to R. Yeah, so these multiplicities are our famous lattice indices, so to say. Well, they come with additional weight correction, of course, but these are the lattice indices we've been talking about all the time. And we sum up those lattice indices of our inverse images. And the statement is this is constant. That is the big statement. Meaning that it does not depend on my choice of P in the image, as long as I pick P away from my walls on which nasty things might happen. But those walls are of smaller codimension, right? So I have a big variety of points. I have top dimensional choice of points in which I can pick my Qs, and then all the Ps will be in the relative interior of top dimensional cones, and then I can measure my degree at this Q, count inverse images of Q with my lattice index, and I will get something constant, no matter where I did the measurement. And why is this so important? Where are we going, right? This is what I want you to see before we stop for the next lecture. We're going to talk about the situation where this is the evaluation map, this is our tropical space of stable maps, and this is just R2 to the something, right? And then we deduce that the degree of the evaluation map is constant, meaning that it doesn't matter where we put our points. If we count tropical curves through those points, we always get the same number, where we have to count our tropical curves, of course, with a certain multiplicity. And that multiplicity at the moment is this lattice index. And of course, I have to still show you that this lattice index is actually what we always claimed that it should be for our tropical curves. So this is what we'll do. We'll continue with this next time. I think I'll tell you a little bit about the proof, certainly, because I prepared the proof already quite a bit with what we've done today. Yeah, and then we have a well-defined intersection theoretic notion of our tropical plane curve count. Yeah, good. So I think this is a great moment to stop. And thank you.